Right? So that we can get into the nitty-gritty of what you guys do and try to tease out differences between your approach and that of the currently established approach, which is statistical, analysis, right? So, and let's take within that, let's take the problem of sentence completion. Okay, so today sentence completion is done through brute force, right? And I see the manifestations of the brute force in the following way. Brute force means, I think they collect lots. For example, even more specifically, as far as sentence completion, let's look at Google's sentence completion within Gmail. All right. So there's a setting where you can say, yes, please help me complete my sentence because I don't have time, or you can turn it off. I turned it off immediately because it was way too annoying. But it also has it does a red underline if it's a typo, right? Or it's misspelling, fine, that's good, it's useful. But then it does a blue underline when it thinks that your sentence is weird. And even though it is grammatically correct, probably it might not be what you wanted to write, right? And so from there, you can tell that the reason why it's doing the blue is because that phrasing is not normal, meaning a lot more phrasings are not like that than like that, right? For example, you can say, let's do a meeting tomorrow, right? And it's just, let's have a meeting tomorrow. But let's do a meeting there's a nuance between the two that I would like to use. And there are lots and lots of examples like that, right? So that's an example of where it's using purely statistical, because the vast majority of the things it has seen are, let's have a meeting. It says, maybe you wanted to say, let's have a meeting, okay? So I'm laying this out for the audience so that they understand what I mean when I say statistically informed algorithms. So not that I'm not going to ask you to tell me how you would solve that necessarily, in your model, but how are you different, if that's the key difference? How you or it's an interesting difference to point out, to highlight what you guys do between what you do and say that particular way of going about things, which is statistically informed.
It might be easier to talk about how we're creating the model first.
Yeah, go for it.
And then diving in. So early we talked about finding all of the distinctions of theoretical interest in a data set. Mm-hmm. That differs entirely from just finding examples of what you're looking for so that you can learn the statistical weights within that data set. So when you find all distinctions in theoretical interest, you're able to take that and structure it in a way that basically mimics the flow of context within the data set. We talk about context a lot with how we build our models, and the way that we've approached this is, at least in language, context is constituted by distinctive word combinations. So when you think of what is the context of a sentence, there are certain words that are happening in combination that give that sentence its meaning. In order doesn't matter, that there are certain ways that words are used, but it's the words in combination that are carrying the weight of what is it that's being said. So by focusing on finding distinctive word combinations, the word combinations that are making a set of data unique or distinctive is what we're structuring within our model. So once you have these distinctive word combinations and you structure them, there is no difference in the meaning of the sentence, let's set a meeting, or what if we set a meeting, right? The words that are being used are happening in combination in a way that is predictable.
Okay, so are you using statistical methods behind the scene, or are you introducing some semantics, or are you what's the the magic, if you can point to it, that tells me that, hey, this is what's driving, I can tell you that what's driving the statistical one is the probability of one word following another word having seen what what we have seen so far, and hence the importance of feeding it as much as possible, right? So what happened before, what happened after, and this is at the word level, and also at the coincidence of those words within within, say, a category or classifications, right? So if certain words or certain clusters of words, or certain sequences of words happen to be closer to each other when we're talking about, I don't know, the category of, like the example of blinking lights. So people ask about blinking lights, right? So if you see, all these colors, green, yellow, and you see blinking, and you see lights, and you see rapid, and they all happen and at a higher frequency, and they all belong together. Those sentences belong to one category, which is, oh, they're asking about lights, right? And then you see another category which has to do with, you know, the quality of my Wi-Fi is not good, and I'm getting intermittence, and you see the frequency of those coinciding, so it created clusters, right? Then you say, oh, it's over there. So there it's distances between words, and distances between sentences, and so on. And I understand that mechanism, right? In your case, what is the glue, or what was the thread that's allowing us to go about doing, let's say, if you want to solve the problem of saying this sentence, it belongs to this category, and therefore provided this answer, just to point to a concrete
Sure.
problem.
So when we approach it, or approach any problem, we're not approaching it with any assumptions of what classifications matter. So in your example of blinking lights, we're not going to go ahead and label all colors or all ways that something might be blinking, or be written as blinking. Our method is actually very similar. It's analogous to the self-supervised learning method, where we make no assumptions and we are continuously looking at the data with respect to, say, a random representation of that data, and seeing what patterns or what distinctions can be made with respect to something that might appear random, right? So if it's, we're saying that anything that is above random should be theoretically interesting, that there's a pattern that exists there. And so once you have all of these patterns laid out and structured within a model, you can then see within different segments of the model clusters like what you're saying, because they're going to erect themselves naturally. Blinking lights will occur within the same contexts, just differing in type, or type's probably too broad, but differing in exactly the instance of color, or the instance of speed of blinking. Things like that aren't carrying the day for context. They're simply the specifics of what might occur within a set of more common contexts.
Okay. All right. So maybe I'm just trying to get it to a point where I can say I grasp it. So the ontology of, let's say, the first, let's call it the predominant algorithm, are words, right? Those words have properties, and then sets, right? That's another object, right? So that's the ontology, and then there are functions that are applied to these, to these objects, and then there are properties that these categories have with each other. So a category or a group contains a bunch of sentences which are themselves made up of words. So that's sort of the ontology there, right? These are the things that are manipulated. And these translate in, when you turn into a computer program, an algorithm, into data structures and algorithms, and also and the words, and they have properties, which is assign it a statistical number when we compare two words, and so on and so forth. So you see where once you define how you slice the world, right, you can do things with it. How do you guys slice the world? Say for this example of where you're trying to complete a sentence. What are the elements of your of the ontology?
So you're right with saying that words, sentences, I'd go as far as documents or even books, you have different containers that you're considering on the front end before you feed the algorithm, before you start training. You have the smallest elements, which being words, and then you have word combinations, right? So you're slowly building these n-grams that are helping you understand the context, helping you understand what is happening within whatever the container you began with.
Mm-hmm.
As you structure those based on how those n-grams are contributing to context, you begin to have a growing sequence of word combinations that are, the larger that it grows, the more likely you're going to end at a very specific n-gram, right? Every concurrent n-gram is leading to a more likely n-gram, right? Because certain things aren't going to be said once the context has been set,
Okay.
right? So
yeah, I'm starting to understand. So let's do like a little exercise if possible, right?
okay.
Let's say somebody let's say I have an algorithm. Let's say your black box, right? And then your black box has seen so far folks asking about the blinking lights problem, right? And the questions so far that have been addressed to it are, I see a red blinking light. And another one says, I see lots of blinking lights. Another one says, I see white blinking lights. Let's say variations of these have been seen. But somebody comes in and says, the green light keeps on blinking, right? Oh, well, no, sorry. The green light keeps on flashing. So green, you haven't seen it, and flash, you haven't seen it. But you've seen somebody talk about blinking red lights. So how would you take that and say, I'm not going to choke on this. Here's how I'm not going to choke on it. How would you not choke on it?
So we haven't approached this problem. Starting out, we've said, if it exists in the data set, we will be able to find a place for it within our models. So if green has never existed, if flashing has never existed, our model in its rawest form does not react to those new words, those new introduced elements. One, and this is theoretical because we haven't attempted this, but I would imagine that given a large enough data set, whether or not it is relevant to this specific use case, you might be able, through the finding of distinctions in that large data set, you might be able to start drawing associations, as we were saying earlier, between flashing and blinking, or red and green once flashing or blinking has been set. So we definitely can't do anything with it if it has not existed in the data set. But given it does exist in the data set, there is likely a path to seeing that those two words or two word pairs are related in some clear way.
So you're not using an external semantic mapper that says blink?
Not yet, no. And we certainly could add it as kind of an inference layer on top of the raw model. But
is the fact that you're not using it, is that in principle, or just you didn't get to it? Meaning, do you plan to solve the problem without needing to lean on the semantic representations?
That would be ideal. And so far in our testing, we have not needed it, but that does not mean that at some point for more complex problems, we will never need it. It's certainly something we can consider. It just depends on what is the use case, what is the end goal of building one of these models.
Okay, so is because now maybe I've been unfair in focusing on similarities as opposed to differences. Would you say that your method is able to say that this thing doesn't belong in this category as opposed to this thing belong in this category? Is that sort of the engine that is driving you guys, and you're hoping that you'll get enough traction with that so that you don't need as much data? So let's say, for example, you have this covered. I know you're saying you don't announce categories. Let's say you've got enough data and you have discovered that there are 3 categories. Would that be fair to say, or am I mistaken?
So potentially, I'd say right now we are definitely looking at nameless categories so that they're empty. They are differentiated within the model, but they do not have labels.
Yeah, no labels. Let's say,
Similar to like how self-supervised learning works, you can add a supervised layer after the fact, right? Where you're adding classifications that might help. So, and all I'm going for is that is something that we are capable of doing, is adding that second layer that if a human has seen that and knows exactly what they're looking at, we can also train the model or teach the model those things.
Yeah, well, let's keep the, go ahead, Ben.
I just want to interject quickly. I'm going to use an analogy. The way a child learns language far earlier than learning the concept of noun, verb, adjective. We just learn it through, it's a combination of through repetition, but then, sorry, I need to say this carefully. We learn it through repetition, but with what is behind our thinking is going after distinctions. I apologize. I should not have interjected. I don't know if we can cut that out. I want to say that the way a child learns language long before learning categories of noun, verb, adjective, they learn it through repetition, but then also with their natural curiosity that would recognize this is different from that.
Yeah.
And I guess I apologize, I'm messing up our call right now because
no, you're fine.
I had something to say and I've lost it.
It's okay. Let me go back to. I'm sure you'll come back as I sort of take a step back, because I don't want to go to. We'll get to the point where, hey, if we add these 3 things, then it'll be perfect and whatever. But I want to stay in the pure form of the thing, right? So you're saying that you have a bunch of data came in. The thing categorizes, doesn't create labels on these categories, right? And the main thing that's informing and driving its categorization, labelless categorization, is differences, right? Distinctions, right? So this thing is not the same as this thing, and so it belongs here. So my question is, how does it say that these 2 things belong together? Is it just because it doesn't belong with any of the other ones more than it doesn't belong to these guys? Is it like?
And so right, the earlier, and this was maybe 30 minutes ago, Ben was saying that neural networks are able to draw connections for the purpose of producing habits better than us. And I don't know that that's true. And it's applicable here because the distinctive combinations that we've been talking about, they exist in containers, right? The original containers that we're looking at naturally. So the data coming in has a natural shape. It has this natural association that is allowing for us to identify distinctions while taking into account the shape of the incoming containers.
Okay. So and so you end up with clusters that you created as a result of having focused on differences as opposed to similarities, right? Okay, and then those differences are what makes a different? Let's say there is A, B, and C, and A is more different than B than it is to C. Okay, I'm assuming that's sort of kind of at the molecular level how things are going. So you have A, and there's B, and there's C. It's saying I'm more different from B than to C. Right? And if I have lots of other things, and A is different from C and D and E, and then B, then A and B sort of belong together because they are least dissimilar. Is that right? Is that a way to do it? Okay. And so how do you do dissimilarity without having properties? How do you measure distance between A and B? Is it not just another way of saying similarity to a certain extent, or is it I'm missing something here? What is the difference between similarity and dissimilarity? You know, other than dissimilarity is 1 minus similarity, if we were doing statistics.
I think it's just that. Like we're just looking at dissimilarity in word combinations.
Word combinations, okay.
So,
okay.
right, and the similarity is taken into account by the natural shape of the incoming data.
Okay, so the sequence blue blinking lights and blue flashing lights, right? Between the two, there's one difference, right? And when it says blue and orange balls, right? Well, this one is different from the other two. Is that right? And you're looking at it that way, sort
Right.
of
So
saying,
the first two would definitely be correlated in some way because they do share similarities naturally in that they're sharing elements. But the third one would have no similarity because our model doesn't know anything about color or all or light.
Or I guess I'm trying to understand, because the first one, distance between the dissimilarity between the first one and second one, and the second one, sorry, between the first one and third one. So the first one is the blue blinking lights, the second one is blue flashing lights, third one is blue and orange balls, right? So the first one, the similarity between this one and the third is greater than the similarity between the first one and the second one.
Correct.
Yeah.
Right? And therefore,
part of the way our models work is we're generally looking at slightly larger containers. So blue flashing light, blue blinking light, given however we've ingested what the source we're ingesting this data from, if this is Q&A for some kind of a hardware problem, that's going to be, there are going to be a lot of other verbs and nouns and adjectives distinctively used about the hardware problems. If we're talking about balls get used in a, they're going to be associated with words like play, game, etc. So part of the strength of this is looking at the broader contexts, and how are we going to overcome a blinking versus flashing thing if what we're running, if the containers going in, these are grouped as conversations. Let's say we're feeding it with Q&A with tech support. A technician is going to know that blinking and flashing are synonymous, and is going to then recommend this is what the probable issue is. So it's other data that in the training data, it's going to show up both blinking and flashing are associated with X problem, where another colored light that might be associated with a totally different set. So the blinking and flashing, I think that's just not going to it's probably not going to show up as distinguished in the training data. So in that, it's not going to, blinking versus flashing isn't going to help us discriminate among subsets of the training data. So I don't see, if we're focusing on very narrow phrases, where part of the strength is focusing on broader containers. So if we're looking at sentence completion, those are tough because if you're dealing with very short sentences, that's not very easy. But if we're dealing with longer sentences, the more words we've got to work with, the more likely we're going to distinguish what's unique about the context that comes out as a sentence goes on, and be able to give very precise responses towards the end. And because we're going by difference, dissimilarity is what drives this. We can get these precise responses off of very little.
I think I'm understanding. And also it provides with the way, I think, to learn, right? So let's say I don't know, let's say I'm somebody who just immigrated to Quebec, right? And in Quebec, they have certain weird words they use even in English, let's say, maybe, and vice versa, right? And then they say, and then I'm a support person, and I'm getting these calls, and somebody says, I see blue flashing lights, blue blinking lights. I know what those means. And then all of a sudden they use something. I see these blue groking lights. All right, and I've never heard of that word. But because I'm smart enough to say, oh, probably it means flashing, right? All of a sudden, I've learned this word called groking, which I've never seen before, and I'm going to add it to my vocabulary, and I have learned something, right? Because it's different, but at the same time, it falls within a category, and the difference didn't trip me. Is that sort of the strength of what you guys are providing, is how to leverage difference, and beyond that, not to be tripped by difference, as opposed to the other one, which really looks constantly for similarities between categories and so forth?
I think that is our biggest strength. So when we are looking at a data set, I was saying earlier, we find all distinctions of theoretical interests, and then we structure that within one of our models. What is nice about this structure that is, totally different from how a neural network is structured, is that because we're starting with context, and because we're predicting, from one set of context to the next, increasing sequences of context. If you have something that is, let's just say, an outlier, so something you've never seen before, and something that is behaving differently than anything you've seen before, there will be a place within the model because it is occurring in combination with other contexts. So no matter the outlier, and no matter the new distinction that needs to be made, there's a place within the model that we can fit it.
Okay. I think we've gone deeply enough for the audience. Probably their eyes have glazed over a long time ago. But hopefully in your page, when we publish this, we'll add a couple of articles so they can go and read some more and get in depth, because this is trying to go deep by just talking, and we can only go so far, right?
Sure.
Especially with somebody like me who's not very well versed. You guys have all these categories in your head, and you're like, why doesn't he understand this? It's obvious, right? So before we go, the hour is up, and is it? Wow. Okay. Well, it went by very fast for me. I don't know about you. But I just want to ask about you guys are, Ben, you are with Atlantic Merchant Capital Investors. Can you tell me a little bit about that and what you guys focus on?
That's our family office. So I manage investments on behalf of the family, largely community banks, some real estate, tech. Trying to think what are our other major buckets of investments. Just a range. We had a taco restaurant, all kinds of. We no longer own that one, but a wide variety of investments, largely picked up along the way from relationships we've developed, and then our father's career as a serial entrepreneur. So always an interesting variety of investments. And
then Sam, you're founder of, how do I say it? Eidetic Ventures. What do you guys do there?
So it's my venture capital firm. I started it about a year ago, and we look primarily in emerging technology investments, or companies that are working in emerging technology. The thesis that I've been working from has primarily focused on companies that are building data assets, and then either applying one of three technology types. So machine learning, blockchain, or quantum computing.
Okay, what is quantum computing?
So quantum computing is, it's an emerging style of computation. It takes advantage of certain characteristics within quantum physics that allow for you to compute more data simultaneously than the classical approach. It uses a fundamental, it's not a bit, it's called a qubit, and it's able to take far more data into account at a single moment than a bit can.
Yeah, and is it still in the labs mainly, or are we seeing it more?
It is still in the labs when it comes to scale. Although I know Google last week was publishing some breakthroughs that they've made. There have been successful computations that have outperformed anything that a classical computer could do, but nothing at a scale that is ready for industry.
And you think how long?
We're probably 5 to 10 years out before we start seeing the entire quantum industry ramp up, but I think it's highly probable within that time period.
Okay. And last question is, can I ask you about Fisher Fox Films?
It's funny, we were talking about that this morning. It was a single investment in a film that was produced by one of our LPs related to Atlantic Merchant. They decided to go into filmmaking, and they've done 3 films so far, I think, and we joined their second one. It was the movie Inheritance, and it starred Lily Collins and Simon Pegg. I think it's on Amazon, so I recommend if you would like to watch a thriller.
What is that? Is that a comedy, or is it?
No, it's a thriller, I think, is the right genre, and it's about a family where the father left. He passes away, and his inheritance turns out to include a man that he has kept captive for many years, and so it's the unfolding of his daughter realizing what he's done.
I'll check it out. I mentioned it because I'm hunting around for somebody who can help me on this project. So you've heard of Alexa, right? Obviously, Amazon Alexa, right? And there's maybe you haven't heard about how these moms whose kids are called Alexa has had their lives turned upside down in a very dramatic way, right? So for us who are not involved, we might find it amusing and all that, but it's real, right? Serious and so forth and all. And so there's this whole movement. It's fascinating because I think it may be a representative of the future, this clash between robots who are starting to invade our life world, right? For example, names of human beings, right? So Siri and all that, okay, fine. But when you have millions of people saying, Alexa, 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 do this for me. Alexa, do that for me. You can easily imagine how, if you're a 12-year-old girl, how boys would be saying nasty things like, Alexa, do X, and X is a nasty thing, right? Ha, ha, ha. And then a girl becoming traumatized over it. So I raise that because I'm hunting around, looking around for somebody who might be interested in doing a documentary. So I'll talk to you, since you are an aficionado and an entrepreneur in that world.
I'm sure I could make an introduction.
How do they call it? Impresario. They're an impresario.
I don't know.
All right, wonderful, guys. This was a lot of fun for me. I know I grilled you, and thank you so much for putting up with me. Hopefully, the audience will be curious enough to follow through with reading about this. Again, if you guys can give me some links, so I guarantee you a lot of people will be interested in what you guys are doing. And if you are making the proposition that you believe you have something that competes for real against statistical model, and there's a lot of negative stuff now being said about the statistical model. For example, I'll send you a link if you haven't seen it, this conversation with Noam Chomsky, who is extremely against this. He says this is not the way to solve things as far as AI is concerned. This heavy data, we're sort of abusing the resources that we have, because it takes a lot of energy to collect all that data, when we should be putting all those billions of dollars into something that's far smarter, if we put our heads to it. Anyway, so I think you guys are onto something for sure. And thank you again for making the time.
Thank you for hosting us, and
Thank you.
thanks for putting up with our first attempt at putting all of this into words.
Well, it's hard.
Into
It's hard,
spoken words,
Language,
learning
like
about things is
Wittgenstein
difficult.
said, right? It's very, at some point you need to stop talking and go and do and prove. It's hard.
Yes.
All right, guys. Thank you so much.
Thank you.
See you.
Bye-bye.